Okay, so I'm going to quickly go over the laws from Chemistry 1, remind you what each scientist said, what their formulas look like, and if you want to get a note card out at this moment and maybe pause the video as we go through so you have all the formulas in one place, I would suggest that. So right now, if you have a note card, write Boyle's Law on it, get his formula down, and then continue on. Once you get to the next formula, pause it and do the same. So Boyle's Law, out of all the scientists we're going to talk about, his two variables that he studied, they were inversely related. He looked at pressure and volume. So Boyle said if you increase the pressure of something, the volume goes down. If you and when I say of something, I mean of a gas. If you decrease the pressure, then the volume goes up. I believe he has a photo on the next part. So if we look down here, our volume increases, and the volume is represented by the edges of this box. So you can see pressure decreases because pressure is when we have collisions with the wall. Well, since the volume of the box is bigger, they have to travel farther. They're not hitting the walls as often, and therefore the pressure is lowered. You can also think about diving. If you were to go deep diving, the pressure on your lungs would increase the farther down you go. And so when your lung volume is decreasing, you don't have as much gas. So it can be very dangerous. Now you can also look up Cartesian divers or maybe marshmallow syringes if you want more ideas or concrete examples. Okay, next we have Charles's Law. Charles looked at volume and temperature. So if you think about it, if you go up to a gas and you bump up the temperature on that gas, what's going to happen to the volume? The volume should get bigger. So these two are directly related. Here he has this formula, but if you don't like things on the denominator, you can also rearrange it to be this formula. It's really up to you. It doesn't really matter. But one goes up, the other goes up. One goes down, the other goes down. If you look at this graph right here, he's trying to show you that as temperature goes up, volume goes up. Now this is of an ideal gas, and you can see this little line right here where it says real gas. The reason is ideal gases, we assume that they have zero volume. Well, think about any gas. The particles of that gas, even though they're small, they are going to have volume, so it's not quite as straight of a line. But as far as Charles goes, know that they are directly related. They do what the other does. All right. Next we have Gay-Lussac's Law. If temperature goes up, pressure goes up. If temperature goes down, pressure goes down. Temperature is making these particles move faster. Notice the longer arrows. The faster they move, the more collisions with the sides of the walls. Let's see if this formula is in here. It's not, but if you want to write down Gay-Lussac's Law, you can say, I use 1s and 2s usually. Temperature 1, pressure 2 equals temperature 2, pressure 1. He uses I's and F's for initial and final. I use 1s and 2s for initial and final. Okay. Combined gas law combines Boyle's, Charles, and Gay-Lussac's. That way you just need to know one gas law. You do need to know these formulas, so it might be easier just to memorize this one. Another way to write it is P1 V1 1 T2 equals P2 V2 T1. So either way, and let's say you have a situation where pressure stays constant throughout a problem, then you can just ignore these. And now you're left with V1 T2 equals V2 T1. Or you could plug in the same number on both sides, but they'll cancel out. So it might be easier just to know this, and whatever's staying constant, take it out with your thumbs, or plug in the same number on both sides. And the last formula, from Chemistry 1 is called the ideal gas law. And so it takes into account two things, two assumptions. The volume of gas molecules are negligible. So that's like we saw in that graph before. The volume of a gas is 0, but in real life, not so. And the forces between molecules are negligible, meaning the intermolecular forces aren't going to cause the gases to connect and stick together. They're going to be moving constant, randomly, and not attracted to each other. Now, here is the ideal gas law. PV equals nRT. P is pressure. We want to make sure that it's in atmospheres for this formula. V is volume. We want to make sure that's in liters. N is moles. R is a constant. Most of the time, R is going to be 0.0821. And then T is temperature in kelvins. And the units for R, okay, are going to be atmospheres times liters over moles times kelvins. And so you can see, because this R has these units, pressure has to be in atmosphere. Volume has to be in liters. N is always going to be in moles, and temperature has to be in kelvins. This R will be given to you on any assessments, but this formula will not be given to you. All right, and they're just restating what we talked about. So I'm going to pause this here. That's the end of the review from Chemistry 1. I think everything from here on out might be new stuff.